Good morning, students. Can you guys hear me? Are you well? Appreciate Michael, Kit, Fabio. Perfect. Just make sure you have your notebook, pen, and calculator, because you will be solving some problems today. Good morning, Lucio de Jesus Venancio Cruz da Fonseca.
Good morning, sir.
How's it, man?
I'm okay. Thank you. Yourself, sir.
I'm fine, man. Guys, in 5 minutes' time, I'm gonna immediately begin. People should be here on time anyway. So by 5 minutes past, we're gonna proceed. Like I said, make sure you have your calculator, notebook, and pen out because we will be solving some problems. Hopefully we can do it in around an hour, and then I can okay just um
pain. While the carpenter just laughed and walked away, but the twins didn't laugh. They locked in that night.
Um, I'm not sure if you guys can admit, but please admit for me. I think let's begin. Can everyone hear me? Yeah, and can everyone see my screen? Okay, thank you. Cool. Yeah, so I'll begin. So guys, welcome. I'm assuming you watched the rolling bearing lecture as well. And I want us to get through um, some content today. So let me just go back to the textbook here. So the good news is we basically halfway um, through our syllabus, and what you where we are now is chapter 11. Obviously, we're on spur gears, and then we'll move on to chapter 12. We'll be looking at helical and probably bevel. Not sure about worm gears. So that's the next two chapters if those want to work ahead. After that, it's probably going to be between chapter 13 and 14. So I think what's problematic with these chapters, normally you have clutch and brakes in one chapter as part of motion control, but they combine it. So there might be additional notes, and then there'll be probably like chapter 15. So we could say like around 1, 2, 3, there's some other elements here, and then 4. And even this itself has a few elements in. But you could say around 3.5. And again, this is the main textbook. Um, I'd like you to always first start here before you always look at my other additional notes and support, which is, I believe, very useful. Anyway, but anyway, so just know we're on chapter 11. So whatever you need here will be in this chapter. Okay, and the aim is to kind of get through most of the stuff over here. But let's proceed with the lecture. Let's see over here. So I'm going to just share the slides now. Cool. Here we are. So, of course, we're calling it section 3 or chapter 3, whatever. In fact, this should be chapter what? 4, actually, no? Yeah, it's actually 4 for us because, yeah, this should be chapter 4 in our case, the fourth chapter. So we basically halfway. There should be around 6 chapters total. Okay, so let's move on. So overview, yeah, not a big deal. We'll talk about these things as we go along. I do want to say one point. You see gear trains, right? I believe this is covered in mechanics of machines. Is that correct? Before I start, what do you cover in mechanics of machines related to gears? I think I should ask that question. You can unmute your mic and talk to me. Kyle, Leakit, Shaw. What did you cover in mechanics of machines related to gearing? Tumelo? Fabio,
Morning, sir.
how's it? Timna.
I'm
So
good.
so what did you guys?
Um,
Yes.
I think we covered the geometry of the gears, including the things such as the module, calculating the module and the
Perfect.
number of teeth. Yeah, it's a pretty basic stuff.
Okay. You
Yeah.
didn't do gate, and what about gate trains? Because you should have done that as well.
No, we didn't do gear trains.
Okay. So maybe if it's okay, do you have any notes on machines related to that stuff?
No, that was a long time ago. I don't have any notes from back then.
Okay, like you're talking about back then. I'm talking about the latest students. I don't know how old you are. I see. So we did the same thing basically. But anyway, I'm looking for the recent students who did it like last trimester or semester. Okay, anyway, I'm not getting anything, right? So I assume you know certain stuff, but it's fine. So you have to figure certain stuff. So this gear trains part, you guys will have to kind of self-study because I believe that should have covered. I will cover everything else basically listed here. Gear trains, you can figure that out. So yeah, let's move on. Cool. So there's a lot to say, right? And I'll share things in different documents which I'll share with you. But we're all familiar with what a gear is. It's like the component which represents I guess mechanical, or the old version of mechanical. We've got different types of gears, which I'll show you in another document. But where I want to come in is this, right? So we did talk about different transmission systems in terms of belt drive, chain, and then gearing systems. And obviously with gears, when you require smaller distances, and there's a few other benefits of gearing systems. But in relation to this, right, the main ones, and there's quite a few different types of gearing systems, right? And I hope you watched that video before Fabio sent it. What we'll be looking at is spur and helical, right? There's also bevel and worm gears. So those are like the four main types of gears you should know. I mean, even rack and pinion is quite popular. I'm sure you've seen this on, a gate, electronic gate, where you'll see the gate move across, electronic, as you click the button, it moves across the thing. It's a very common type of setup. So as long as you are able to lease on a basic fundamental level, spur, helical, bevel, and your worm gear, then that's okay, right? That's the objective for this thing. So let me just quickly go over this. I just want to share another document which I find a lot better. And then we're gonna don't spend too much time talking about, but I think it's of course necessary. And all these notes I'll share with you. Let me just open this one up. So this is, I'll just read through this. It's based on Shigley. Yeah, spur gears again have teeth parallel to the axis of rotation, and they're used to transmit motion from one shaft to another, two parallel shafts, right? Helical gears are nearly like spur gears. The only difference is that the teeth are inclined, right? And they're also not less noisy due to the orientation of the teeth. But what they can also do is they can do parallel and non-parallel gears. Okay. So your bevel gears, which is over here, if you're not familiar, the teeth have what's conical surfaces, and they mostly transmit motion between two intersecting shafts, or shafts in two not parallel, perpendicular to each other. So one shaft is turning this way, and we need rotation going that way. We have to use bevel gears. A worm gear, right, says resembles a screw, and obviously they say the direction of the rotation of the worm gear is also called the worm wheel. But let me just show you some case. So this is what a spur gear looks like. It's a basic formation of a gear. teeth is parallel to the axis of rotation and from one parallel shaft to another. Obviously, you know, two different sizes. There are some applications of that where these gears are. You also have your internal, external spur gears as well. And that's just depending on what type of application. This is the most basic gear. The helical gear, the teeth are cut at an angle to the face of the gear. Did mention it's more smooth and quiet, more than spur gear, and also it can carry more load, right? There's actually another component there. So these are an examples of helical gears over here. So I'm sure you've seen these before. So that's the difference there. You've got herringbone gears, which is nearly a type of healing gear, and they're used definitely in heavy type machinery. I'll show you some more pictures as well. Got the rack and pinion, right, which is I think kind of standard. Then you've got your bevel gears and are useful when the direction of shafts rotation needs to be changed. And typically the shafts are mounted 90 degrees to each other. There are other types like your straight spiral and upward. There's a few applications I want to show you. So these are what bevel gears look like. Okay, as you can see over there. You've got your worms, and they basically mostly used for a few things, but one of the essential ones is the large gear reductions, right? So you want to have a big reduction in torque transmission or things like that. The same many worm gears have an interesting property that no other gear set has, that the worm can easily turn the gear, but the gear cannot turn the worm. So typically, you know, we can do it the other way around. We have the gear turning the so-called small one or the pinion, and yeah, so there's that type of worm gear. So all these things is more about, you know, application. This was another cool one I saw. I like this. I'll share this note for you. I'm sure we've all seen this before. And we've all seen this element here. Here we have a rack and pinion over here. This is another type as well. Sure, we've seen all of this before as well. This is now this avoid. I don't know what this is. It's what transmission this is. It's on a propeller or something. But here we have a planetary type of internal gear. We'll talk about maybe that. Here is some massive helical or herringbone gears, double helical, right? So these are again heavy machinery, like I mentioned. Your standard gearbox will have a lot of helical gears as well. And then the apparently of this motorcycle, they use spur gears. Then I'll just probably show you over here. I'll share this particular note with you. I found quite good. That's a straight bevel. That's a differential of automobile. We have different intersecting of shafts. And okay, cool. Then you have your worm over here, and that's of a basic of a crane. So we have the worm, and then we have the other thing. So obviously a lot of applications of gears. And the main core focus of this particular, I guess, chapter is that. Just want to admit these people here. Is that we know how to design gear. So we're not looking at gearing systems, so to say, but the individual gear, like how do we make sure it works? And I'll mention something afterwards. I mean, nowadays we are at a point of 3D printing gears, not obviously of steel, or what we can do is generate gear, send it to a machine shop, and they can manufacture the gear for us depending on the application, or we can just buy what's already on the shelves. So I think what's also important here is just having an understanding of different gearing type systems, and then obviously possibly how to design them. But there are many possibilities that can happen, but it just depends on where you work. Okay, so just looking at the different types and then the advantages and disadvantages. Now, just want to highlight you the main ones. Spur gear, standard velocity, pitch line velocity is less than 20 meters per second. That's your R times omega. Right? Very noisy, specialized speed. Helical gears, that's where it got kind of developed. Someone figured out, let's take spur to helical. And it gives us higher speeds. That's the first thing. However, the only problem is we get a thrust load on a single phase, which means on the shaft itself, there's an additional axial load, right? So like here, you have a radial load, now you have an axial and radial load. And this is again talking to the bearings, right? So maybe you want to perhaps use roller bearings, that's the case on our shaft. Bevel, right? 90-degree shafts. But then what's important here is shaft alignment is critical. Obviously, rolling element bearings are therefore often used, right? We can't use the journals, obviously, and also limits power transfer in high speed applications. Again, can be expensive. Obviously, the more engineering gets involved, the more price it becomes. The worm gear, again, compact, cost effective for large gear ratios, like I said. But there is where by abrasion also can generate very high thrust loads, and worm cannot be driven by the gear. Only the worm must drive everything. It's a one-way relationship in this case. So these are the basic disadvantages. And like I said, these things typically will probably be installed. But I mean, what the core focus of this next few things is just looking at the forces on the gears. How do you design the gear? More than a gearing system, if that could make sense, like a gearbox or that's kind of covered. I mean, supposed to be covered in mechanical machines. Cool. So there's a few things, right? And what I want to rather do is just go to the other slide. But what is key, just in terms of terminology, we have a driver gear. It's typically coupled to a shaft motor. We have a driven gear. I believe you all know how gears move relative to each other. Secondly, we call the driver gear the pinion, and then we call the driven gear the gear. It's just useful to label this. Then I want us to go to all this nomenclature over here, right? Explaining what all of this is. So this is, you kind of have to know it, especially for the early stages of this thing. But eventually you get used to it when you apply the formulas. So let's quickly just have a look at that. Just going back to that other slide, which is a bit better in my opinion. Okay, why can't I move this here? There we go. Let's go to this one. Yeah. So over here, there's a few things, right? Again, both books do it. Shigley, just move him over here. So this is the general nomenclature, right? So one of the main ones is the pitch circle, right? Which is essentially over there, right? It's kind of like midway between the two teeth. I hope everyone can see that. Let me just zoom in a bit. That's your pitch circle. It's very important because that's related to something with your pitch diameter, which is a very important parameter when it comes to the module over here. But right, let's say the pinion is the smaller of the two. We've talked about this. The large one is often called the gear. We've got something called the circular pitch, which is from one side of the tooth to the next, from one tooth to the next tooth starting. That's called a circular pitch. You can think of it as an arc. Remember your range measure. It says from point on one tooth to the corresponding point on adjacent tooth, right? And what's important there, it is equal to the sum of the tooth thickness and the width of space. Very interesting, right? The tooth thickness, you see there? And your width of space, okay? Don't feel overwhelmed. Remember, it's open book, so all these things you can probably just have a look as long as you have an idea what's going on. M, the most important thing, right, is a module. And that's the ratio of the pitch diameter to the number of teeth, which is this over here. This is of utmost importance. If the module is not the same for any gearing system, it will not work. So your module is very important. It's a term you will use in gearing all the time, module, right? It's of utmost importance. And it must be the same. And we will embark on that. Your diametrical pitch is essentially a ratio of your number of teeth to the pitch diameter, which is this over here, right? So not this, yeah. And diametrical pitch it's your pitch circle. Okay, it's just some kind of ratio. There is other things as well. Let me just quickly see your addendum, which is from your pitch circle going up. That's your addendum, right? Cool. Typically, it's 1 times a module, and these are like typical standard things for a particular pressure angle over here, but we'll talk about that. Your D-addendum, in this case, is going from the pitch circle going down. So that's easy to remember, right? And you can already see some obvious things which comes up to play, like addendum and D-addendum gives you basically the height of your tooth, so to say. Then we have your clearance circle. Your clearance over there from where the actual what is this like? You know, your okay, there's also your D-addendum circle at the bottom here. You'll notice your D-addendum circle is starting at the D-addendum, then your addendum circle starting there on top. But there's this difference which is called the clearance. It's all important, especially when it comes to measuring of gears. Your clearance is the amount by which your D-addendum in a given gear exceeds the addendum, right? That's what that is. That's your clearance circle. Where is that one? That's your clearance. And your clearance circle somewhere else. Then a backlash is something that's very important, but we'll talk about that again. Yeah. So there are a few terminologies in terms of gearing one must be just comfortable with. But as you apply the questions, it kind of becomes fairly easy. And obviously the face width of the tooth, which is a very important thing. Okay. Then what I'll do now is just revert back to the slide, and you'll start to see if I need to come back to this. I want to get to solving problems. So yeah, so anyway, over here, yeah, so then again, you can have a look at this. Another key important thing you want to have as well is something called is your center distance between two gears, right? And which is fairly simple. And the center distance, no, why is it thrown over here? But it's essentially your one radius plus your other radius, right? So if you're looking at this particular sketch, it's R1 plus R2 will give you a center distance between the two shafts. So just be aware that's a very important relationship. You can also express that relationship in terms of teeth, right? So that's also very important. This year, know it very well. Just make a note. Because it's obviously the key parameter having the center distance. Again, there's some other things you can look at. I didn't mention the addendum. A and D addendum is a tooth width. There's something called the clearance as well, which is your D addendum minus A, which is the one circle, and then your working depth. But these are not particularly important. The center distance and just knowing what is will help you. Cool. So in terms of the fundamental laws of gearing, again, this should also be covered in machines 3. So I don't want to go too much about this, but obviously as the gear rotates, you get something called an involute profile, involute curve. And that's where the word involute gearing comes from. And I can show you what that looks like quickly. Let me just see if I can do that. I'm going to spend too much time on all of this. Just opening up a slide for you. And that's so-called involute profile. Okay. I'm assuming you guys can see this next slide now, right? And so this is what it's supposed to be about. And well, essentially the law of gearing, and I don't want to talk about too much, but it just states there that the angular velocity of all gears of a mesh gear system must remain constant. And also common, normal at the point contact parts of the pitch point, okay? But this is the involute profile, as you can imagine. So they have 2 gears, right? You've got this pitch point relating there. And as the gear turns, it will actually kind of draw the so-called involute thing, right? You can see there. And that involute profile is of utmost importance, and I'm just want to see if I can find we'll come back to this. Okay, so that's the involute profile over there. Okay, that's cool. I thought I'll find this line, and then you get the next line, and then the next line. So it'll give you some kind of profile. And if you guys are able to see that, let me go back. So this over here. Nevertheless, we can move on. So from that,
Good morning, sir.
yes.
There are people in the group, WhatsApp group. They're saying that they've been struggling to log in, and they're waiting for you to allow them to.
Okay, cool. I'll
Yeah.
do that now. Thanks for that.
Okay.
Appreciate that. Jacob, no? Is that you? Yeah, cool. So let's move on. That should have been here early. That's the thing. So from that, we can look at some other stuff as well. It seems super overwhelming, but it's not. Can you just mute your mic there? Cool. There's a few other things as well. One of the key elements is something called the pressure angle over here, right? And and we'll talk about this line, which is the length of approach. There's some pressure angle, which is very important. But again, when we're looking at this, so your involute will have this profile, there'll be another involute on that other side. Involutes going, sorry. And then there's something called the radius of the base circle, which is important. I think I'll come back to this in your base picture as well. So these I'll come back as I obviously explained. But what's in key is this angle over here, this pressure angle over here. Cool. So when we're looking at getting all relation to all of these things we mentioned, is most gears are cut at a standard pressure angle of 20 degrees or 25, right? Which is to do with this over here. And this is very important. You'll notice we will need this sometimes when you do this gauge geometry, right? Of the base circle and R, which is the actual radius of the main thing. It looks super overwhelming. And then what's important, once you know your angle, you're able to basically pull up all your values from your addendum, maybe 1 times a module. These are all standard systems for teething. Your D-denim should be 1.25 times a module. So this will all assist you when you're designing your actual gearing system. So you don't have to worry too much. The tables are all there. Clearance that much. If you notice, they're all related to the something times a module. You have also 20 degree stub tooth. I'm not sure what that is. Then you have your 25-degree full depth, which is that over there. There is a rule as well, which is very important for gearing systems, but we'll talk about that. Maybe not too important, but that's for the circular pitch. And you breathe every tooth, but don't worry about that. And then there are some other formulas as well. Cool. Again, standard teeth, standard module ranges as well. These are all standard module ranges you can get. Cool. And most widely used is a 20-degree pressure angle. So that's that. So okay. Anyway, with that being said, I'd like us to quickly do a warm up problem, and then we're gonna go into this one, right? And then yeah. So this one is using a basic laws of gearing. Make sure you remember this and write it down. Omega is your rotational speed. N is your number of teeth. D should be your diameters, and there should be torque, if I'm correct. But I'm very skeptical on that. I got to look at the relationships, but these are the basic laws of gearing. Yeah, over here. So I'm not sure it's fully equivalent. Let's just have a look. So let's just quickly angular speed. N is your speed in RPM. Okay, it's the same thing then. So yeah, so let's stick with this one. So and in this case, the denote RS is the gear ratio, right? Let's quickly just copy and paste this one. And what's important there is that your linear velocities are the same. That's a pitch line linear velocity. So I want you guys to quickly do this one for me. All right, warm up. That should be some basics from mechanics 1. So what they want is you've got two gears. You've got a module. I probably should have put that up for you as well. But if the guys are not familiar with a module is, let me find that formula for you. And then you can begin. Your module is, the module is your pitch circle diameter divided by n, which is your number of teeth. Cool. Let's quickly do this one. Yeah. So I want you guys to give me some answers. I'll give you guys around 5 minutes, and then I'll come in and go through the answers of this one. Is that clear to everyone? You can just post your answers in the chat, and or you can just velocity ratio, same as gear ratio. I think it's the same thing, right? Or yeah, I mean, how do you wanna put it? It should be N2 divided by N1, right? I'm just verifying on this side here. It's a bit different. So I think the velocity ratio is just got to check that out though. That's N1 would be the speed. Okay, it depends on how you want to put it though. Okay, but we know that the pinion drives a lot faster than the bigger gear. So let's see if we're able to get that. Just want to see. Cool. Anatia, are you talking? Can't you? Are you talking? Oh, okay.
No, sir.
Okay, sure. Just quickly try that one, right? Guys, when you come to my lectures online or on campus, you're always working through problems. You're practicing for the exam and you just don't even know it. So work. Just trying to figure out something. Yes. Talk to me. So from your module, you can obviously find your pitch circle diameter, right? That's what's important there. And if you have a velocity ratio, that should also assist you with both finding the amount of teeth as well. So that's a few things you can actually get right there on both sides. I don't know why they say velocity ratio like that. It's really confusing. Okay. I'm just gonna prepare this one. Anyone has answers for me? Okay, let's see. So your angular, your velocity ratio should be equal to okay, depends on what you want to call it, but I mean we all should know which one is where. Okay, let me just quickly see. Is there any questions? I mean, is there any answers so far? Sorry. Hey man, sorry about that. Shaw, Anati, Bridget, Emmanuel, Fabio, Camagelo, Kenosi, Kyle, Iziwe. Any answers? Guys, talk, man. Yes, Fabio, talk to me, man. You should just unmute your mic. Yeah. So I think let me just share my
Sir,
OneNote. Yes, talk to me, man.
the answers are in the comment section.
Okay, I'll check now. Thanks, to me. Let me see if I agree with your answers. Where are they? So we have 20 teeth and 720. Let's see. The first question was no, I don't agree with that. Teeth should be not that. 15 teeth, 960. Charles got it, and a velocity of 6.3. Yeah, Charles are main man there. Yeah. We all get Charles' answer. Nicely put there, Charles. Yeah, Jacob's also got it there. Perfect. Yeah. If you got that, well done. So there's no need for me to solve this one. That's fine. Okay. That's a good warm-up.
Yes, I think
Yes.
I got like 15 in terms of speed, the velocity. I couldn't find it. The velocity.
Yeah,
Yeah.
so for your velocity, it'll be the same for both. And therefore, you have to use your V equals omega times R. And if you want to, I'm not sure if you found your module should be equal to your dependent your diameter of your gear or your pinion divided by the number of teeth. So I'm not sure if you have it like, you know what I mean. I'm just using so dp for pinion small, dg for the gear, the bigger one. So obviously it's
Okay.
just this. Yeah. So
So
your RPM. Yeah.
this will help me sort of just get D. Is it D? I don't think so. So
CJ, I
using
cannot
all,
hear you. I cannot hear
I'm
you properly,
saying
my man.
I'm saying using this module ratio, what is it that will I get? How will it help me to sort of just get that V equal to omega times R? Oh, okay. I think maybe I might get R using this module ratio.
Yes.
Yeah, I do
Yeah.
not make that. I already have omega. Okay, I see.
Yeah. Okay, just try. Okay, it'll just a warm up. So let's try and do a bit of yeah, a bit of the stuff we need to do. Now I want us to move through this nicely so we're able to yeah, get through what we need to get through. So let me just put up the next one over here. Okay. Oh well, I can share this. Okay, let me just do it like this. There we go. Yeah. So getting from the textbook, here we are, and let's try to solve this one, right? And what we're going to be using, what I should have, okay, I did mention those what is this? Those the standard denims, but it's you obviously see once we solve it, you know, and guys, if you have any questions as this arises, and then it'll be great for you for us to go back and go see instead of us, you know, I like to talk too much. I like to first do something and then move back. Cool. Let's quickly find the number of, let's read the question and we start to solve. So 2 parallel shafts, which is obviously important. It cannot work if it's not parallel shafts. A and B, with the center distance C, which you're unsure of yet, are to be connected by 12.7 millimeter module, 20 degree pressure angle, and spur gears 1 and 2 providing a velocity ratio of RS, right? What they want is the number of teeth. That's for both. Your radius of your base circle RB, right? That's important. Your outside diameter DO, your clearance F, your pitch line velocity V if K2 rotates at a rotational speed of N2. So that's all the givens. We've given the center distance C over here, and we've given the module, and we've given the pressure angle. Let's see. Design decision, common stock case size are considered. So what is important here, my colleagues, is I want to put this up for you, right? And this is the table you're gonna want to always work with, right? Luckily, you don't have to know this. A lot of engineering work is, yeah. Where is the creativity sometimes? You ask yourself. We use this table over here, right? It will assist us in all these things. And just getting used to the formulas, obviously, even myself, I don't remember all the formulas, man. So I just have to revert back. I'm not a case specialist or anything. Cool. So let's quickly do. So hey, number of teeth. So we know that our module is equal to our pitch circle diameter, right? Divided by the number of teeth. Okay, so I just, you know, G, or I can say I'm going to use small d for pinion, right? I hope you all used to that nomenclature at least. Okay, so n is the number of teeth. In this case, we have the module, but we don't have our diameters, and we don't have the number of teeth. So we're kind of stuck there. Your center distance is equal to dg over 2 plus dp over 2. I think we all understand that, right? That's this radius over here. And then that radius over there. That's R1 plus R2. These are alternative form to this. Are we all happy with that so far? Just getting the relationships there. Are we all content with that? Students?
Okay. Yeah. I sort of
Okay,
that
cool.
makes sense.
Yeah.
Makes sense.
Obviously now they've given us the RS, which is the gear ratio, and it's 1:3. So that's going to help us as well, right? So let's just put that there. And obviously, you know, yeah, there we go. So then now from this, let's see if we are able to solve this. And obviously, with the gear ratio, it should be your R1 divided by your R2 in this case, right? Let me just confirm something here. Yes, we're going to be sorted now. Perfect. Okay. So first things first, we have our center distance of 355.6, right? So we know that C 355.6 is equal to R. Can I just call it R1 plus R2, or we can call it RG and RP. Just don't get lost with that, right? We also know RS, which should be equal to R1 divided by R2, right? That's important. I just want to tell you, colleagues, the way you can remember your velocity, at least your velocity part of your gear ratios is the following way. The pitch line velocities or linear velocities equal to each other. You know that's R1 let me just call this RP times omega P must equal to RG times omega G. And then you know RP divided by RG is equal to omega G divided by omega P. Or so we can call this 1, you know what I mean? So this could be maybe R1 over R2, depending on which you're calling the smaller and bigger. And this will be omega 2 over omega 1. That's one way to remember part of that. Are you guys following me so far? If you're unsure, please tell me. Yeah? I'm just giving you a quick way to perhaps remember, you know what I mean? If you forget, just work with the linear velocities. There is another way to remember the teeth as well. See there? Something like that. T1, D2, omega 2. Yeah, so that's where it comes from. Because the linear velocities are equal. You guys happy with that? Fine. So we know that's R1, so that we know that that's going to be a third equals R1 over R2. I can times that 3 over here. So we have 3R1. And then I have that will equal R2, right? Obviously, our R1 is our pinion, am I right? Is it the small one? Yeah. So it's RP, and this guy is called RG over here. Yeah, just always kind of comfortable working with. Yeah, cool. So what you can just do is obviously just take this into that over there, right? You know what I mean? Substitute this into there and then solve for RG. And then you have the radius of G, and then everything else should kind of work out. Or what you can do is set one equation here. I do, I'll just say RG minus 3RP equals 0. Set another equation, and this will be 1, 1. So setting up a matrix, that's RG, that's R. It's RG, RP. And this is, why are you doing that? Okay, and that's equal to 355.6. And the other one's going to be equal to 0. So you can obviously solve it using determinants as well, or a matrix. And RG is 1, and that's -3. Can do this in your calculator as well. It's entirely up to you. So can we quickly get solving equation 1 and 2 together? Can we get our R's there? So you can do substitution, determinants, matrices, whatever you feel is best. Yeah. Are we all on the same page, colleagues? Right, let me see the chat. Okay. Here's the teams. There we go. Fabio, is this the latest one? Okay, I'm not sure of the answers. I'm gonna have a look now. You have? Oh man. Okay, let's see. Let's close that. How much for the 2 teeth? I'm not sure what your answers there. Eh? Yeah, for the 2 teeth looks good. So what did we get for R1, R2 people? For RG and our RP. What did we get? 2.6, perfect. Shoals on fire there, right? So let's quickly have a look. So for your R1, you should have gotten 88.9, or that's your opinion, right? 88.9. 88.9 millimeters. And your big one will be 3 times more, right? Which will be 266.7. We all get this one. I mean, you should be able to do it. Okay, just check that. Once we have this, we then come to our formula here on top now, right? With our module. So to find the number of teeth for the gear will be easy. Using the module formula, it will simply be dg divided by m. Then we'll have np divided by dp divided by m as well. So that's what we got to do. And our module in this case was given as 12.7. So that'll be 266.67 divided by 12.7. And this will be 88.9 divided by 12.7. Students, are you following me? Yes or no? If you get 21 here. And the other one is? Hey, let me just, oh, my bad. That should have been times 2 times 2. Okay, so this should be 42. And the other one should be, remember, it's diameter times, what is this? And this is 14. Okay, so 14 teeth and 42 teeth over here. Yeah. Okay, I'll give it a minute. Are we all, do we all manage? Yes, I will post this meeting on Blackboard, yeah. Don't worry. Let's first put in some good work here. Yeah. Chat. Guys, you're not saying anything. Do you guys get those values? Yeah, RP Charles got it there. Okay. If that's fine, let's move on. There's no one is saying anything. We've solved the number of teeth. So now we need to compute the radius of the base circle and the outside diameter TO. Cool. So just reverting back to our formulations, and I did mention this radius of the base circle. I'll just quickly show you what it looks like. And I think now's a good time for me to bring that up. Okay. I'll paste it over here. Cool. So let's quickly see. And you'll get the formula now. Just want to have a visual representation so you can actually see where the formula is coming from. So your base circle, like I said to you, is where the gear is, let's just have a look here. So this is RB, right? That's your pitch circle, that there, halfway through the tooth. Here's a pitch circle halfway through the tooth, right? Then you have your base circle over there, okay? And then, which is there, right? And then you have this, yeah, so your pitch circle is at R2 over there, the actual radius there. There we go. And then you have this, your base circle, which is, I thought that your base circle, which would be the one with teeth is rotating. That's what's confusing me. Anyway, so then we need to find, like I said to you, the radius of the base circle RB, which is going to be basically that. And the outside diameter D0, which is that should be your pitch circle from what I understand. But we already have that, which is confusing to me. But looking at the base circle, and you notice it's tangent to the pressure line over there. And then I'm just copying the formula for you here so you can actually see what it looks like. It's going to be this over here, right? So if we look at the formulation of this, it's RB divided by R equals cos theta. Cool. So where is this coming from? Let's have a look. It's over here, right? See this over here? Our R is going all the way, is it over here? That's R, right? You see there? And that's a 90-degree triangle. So we know that that's going to be R, which is the radius, right? The pitch circle radius, which is the main one, which you always work on. And obviously, if you pull up your trigonometry, it's going to be cos theta is this is your hypotenuse, and that's your RB1, RB. Are you guys with me? RB1 divided by that will give you this. So that's your base circle. So once you have your pressure angle and then your R, you should be sorted. And then the outside diameter DO, which from my understanding, have we not solved that? Am I confused about something there? That would be okay. I think the terminology is bothering me. It's with your addendum. Yes, I see. And I want to just show you that as well. So DO, right, would be, I believe that's your addendum circle, man. That's I think the wording is the thing which is getting me here. Okay. So DO would basically be your pitch circle, or your base circle, your radius, and then you got to add the addendum on there. That's what that is. So just why would it be so confused? So it's your base circle, and then you're adding your. Let me just confirm this quickly. Just want to be sure about something. Okay, for now, just work out for me your radius base circle, if you don't mind. Can we quickly get that? Something is just bothering me, man. Just gonna see something here. So radius RB1. Did you guys get for me my radius circle? Is D addendum? Is that what it is? Looking here now. Let me just check. You guys get it? Oh, did you guys get it? Sorry about that. Yeah. So it's quite simple. We're just gonna have to take your respective R times by cos theta for each one. So you're gonna have, you could call it RB1 or RBP. Okay. RB2, which is essentially representing P, and then there, that's that. Just trying to see, I'm still trying to see what this is. I don't know. It's not making sense to me. Okay. Are we winning, guys? Do you use a pitch circle, man? That is why I'm so confused. Yeah, okay, cool. So that D is gonna be your addendum, should be your addendum circle, I believe. Yeah, it's a addendum circle. If I'm correct, let me just confirm. D0. Okay. Just want to see. Yeah. Cool. You guys get the base circle? Just want to see. Ooh. Perfect, right? I think Shaw, that's 83 and 250. Yep, that looks, yeah. So if you get 83, Shaw has 83, it's just hard to toggle. 83.54, yeah. I'll write it down now, 83.54 millimeters. And then your RG is going to be 250.62, perfect, okay. 6.2 millimeters. Now, they're asking for the outside diameter DO, which I believe, if that is your RB, your base circle, that's basically, is it this complete circle over here? But what we're going to require is obviously our addendum, right? That's what's important over here. And for us to do that, it's going to be DP and DG. Okay. Are they asking for diameters or the outside diameter? So that means we already have the one diameter, right? That one diameter is given as, that's what you put in the diameter again. 88.9 times 2 is 177, right? So it's not the pitch circle, it's the one. And we're going to add another piece, and then we're going to have, other one was 266.7 times 2, which is going to be 533.4. And then now, to find, I believe it's this circle over here. So we have the base circle, which is R B over 1. So we need to, I believe, get that part. But now we have to refer to this table over here. And we are dealing with a 20-degree pressure angle. I believe it's a full tooth. And so we need to check over here. And I think if you look at that, HK, which I did not probably specify, is the working depth of the tooth. So your base circle's over here, and then you're gonna have to say, because remember we need the height of the tooth to find that circle over here. So the circle we're talking about is this one over here. You see the one on the outside? I hope everyone follows me here. Let's get this pen. So the circle over here. It's not typically asked for. So we want that circle. So we already have this guy over here, which is the base. And we need now obviously this distance from here to there, right? And luckily that's the height of the tooth. And we can easily pull it from this table. So we know that it's going to be 2 times the module in this case. Okay? Are you guys with me? So then you're just going to say plus 2 times the module, which will be 12.7, and then 2 times 12.7. I'm finding quite strange you're asking for this because normally we always work on a pitch circle for all our values. So anyway, so let's just quickly get those values over there. Yeah. And then once we're done with that, we have to find the clearance, right? Which is your face of your, or your addendum, right? Minus your dedendum minus your addendum, which I think I talked about.
Sorry, sir.
Yes, Chief.
If I said the clearance is equal to 0.25 multiplied by the module, am I wrong?
Nah, you're right, brother. Same thing. Same
It's
thing.
the same thing.
Yeah, and we'll verify it now. Can we just get these answers quickly? Yeah, and the clearance is given over here, right? There we go. We'll talk about it now. So these answers here, or I'll just do the one. It's 558.8 millimeters. Okay, that's that one. Other one you can figure out yourself. So then the next part is the clearance, right? And I like what whoever that was. The clearance could also just simply be, so your clearance F, in this case, it's 0.25 times the module, and you could just say 0.25 times 12.7. There's many ways to do this, and you should get 3.175 millimeters. Well, it's just important here. You'll notice that it's the dedendum minus the addendum, which is not shown in this particular one, but that's that space I showed you before, and you can check over here. So if you look at BD, right? BD is given as your dedendum, which is 1.25 times the module, which is going to be 12.7, and then we're minusing it by the addendum, which is 12.7, and you should get exactly the same answer. So if you follow this formula, so this would be 1.25 m minus m, basically. And obviously this would be 0.25 m. Is it not so? Can you guys see that? So you can just use the table as is. Any questions thus far before we conclude that one? Any questions, guys? Let's quickly get this velocities. You see here, guys can ask questions, 2 or 3, and okay, perfect. Yeah. Are we happy with the addendum and dedendum? Duncan, Jacob, CK, Timna, Emmanuel, Tumelo, Kyle, Malose, Sanele. Guys got that?
Yeah.
All right. Okay, cool. So once that is done, let's quickly close off this one. They're asking us for the pitch line's velocity V if K2 rotates at N2. What I want us to also do, let's try to see if we can find both these let's see the pitch line velocity the same for both. So that's fairly easy. It's V equals omega 2 R2. I think that was given to us, and omega 2 is given as 500 RPM. We can even do pi dn over 60, right? So that's pi times the diameter of number 2, which is our gear, is 533, no? What was it again? 533 something. 533.4. And then our RPMs was given as 500 revs per minute. And we divide that by 60. Okay. Let's get our pitch line velocity for that one. And then can we confirm with omega 1 and R1 as well? What's my pitch line velocity, colleagues? You can unmute your mic.
I'm getting 13.964.
Okay, 13 point. Who is that? 964 what?
964.
Unit? What's a unit? Oh, sorry, that's a long one. Meters per second, right? You guys agree with that one? I'm not sure. It looks quite high, eh? Yeah, that's fine. That looks cool. So how do we find V1? How do we prove that the velocities are the same? Check with everyone. Yeah, that's correct. Thank you for that. What is my RPM of the first one? So for omega 1, or the gear, it's R1 divided by R2 equals omega 2 divided by omega 1. Am I right? So to solve for omega 1, we can do raise everything to the power negative 1. So therefore, this will be R2 over R1 will be equal to omega 1 over. Therefore, omega 1 should be equal to R2 over R1, which is equal to omega 1. And I believe this was 1 over 3, so it's 3 times more, right? I don't know if you guys agree with me. What's proof is that this is spinning faster than the other gear. So 3 times omega 2, and then obviously R1. And then once you have that, you apply the same formula. I want you guys to verify for me. What you must find is that they are exactly the same. The linear velocity is the same.
So can you please go back to the pinion for the radius of the pinion?
No
The
problem.
pitch radius of the pinion.
Yeah, it should be 88.9. There you go. Okay. I'm not sure what that is, but is everyone else following? Guys, best time to ask questions, right? We have 1, 2, 3, 4, 5, 6, I think 7 weeks left. Next week, it's 6 weeks left.
Yeah, I'm still getting the same answer. It's
Oh, there's
13.964.
Perfect. Yeah, it's supposed to be the same. Yeah, that is your piece. Okay. So what I'll do now, I just want to show you guys something, and then if you guys do want to have another lecture tomorrow on this for design 3, it'll be great. So we can get moving. The sooner we get the content done, the better for all of us. So you can focus on other stuff while this is happening. I don't know if that is okay with you guys. And then I want to share something with you guys. I'll share it with the link. Is these cool things which I wanted to play around with. Let me just go to my thing. And yeah, can you guys see my screen? Let's just move this gear, man. Let's go talk. This gear number 3. Can you guys see this over here? Colleagues, can you see all of this?
Yes, sir.
Perfect. So what I want you guys to do is try and fool around, play around with this, change stuff, change amount of teeth. There's so many things you can do over here. Let's just see the number of teeth. I can make it more. I can make it 12. You can see what happens. It automatically changes all of this. It tells you, that your pitch diameter, your diametrical pitch, your pressure angle. You know what I mean? Just play around with this and see. There's another cool one. want to show you here where, okay, it's not this one. There was another one. I want to find it for you. This one, what typically happens out there, if you want to actually create a gear, and what you can actually do, obviously we have this format. I think this is your could be 3D printing format. And you can actually modify your gear here and look what happens when we change the pressure angle. You see there? And we can change the amount of teeth, and it actually will give you a drawing output. And you can actually go print the gear. So let's put in a helix angle. I remember standard helix angles of 12. You see here. So there's some great things you can play around with. And what typically happens is you don't have to like go redraw gears from scratch and things like that. You can normally just play around, check your module, change it to a certain dimension. And then the gears can be printed for whatever reason. There are some other advanced parameters like backlash, clearance. It's a few things. There was another one I wanted to show you. And just go play around with these tools. They're very important. Is it this one? That one. Not this one, sorry. It's another one. So you can try to further understand this is the one. Understand understand gearing systems and things like that. And you will notice important things related to that. So you can see over here, this is a cool one where you can set up different types of gears. You can actually move it on the axis over here. You can increase the speed. Let's go to 100. Try to go to 100. Can't I increase further than that? Let's 10 the max in this one. Okay, 10 is the max in this one. And we can actually see how this one rotates with that one. You can change the module as well. Obviously, we increase the module. It should increase a few things. It's going to load up now. Yeah, there we go. And we can obviously add gears, remove gears, things like that. We can set a compound gear if you want. And all of this is essentially programmed, and then it kind of figures out, you know what I mean? So nowadays, designing a gear from scratch is not what's going to happen. Is that you normally have all these cool tools which are found, and you can generate gears, set up a drawing, send it to the manufacturer, unless you're the guy and you can actually manufacture the gear, and all the dimensions are right for the gear. But yeah, so I'll send you this, try to play around with it, see what you can learn from it. Let me know if you found something interesting. But I'd like to just let me know. I want to just, if it's cool, Fabio, probably create a poll. If it's okay, not okay, no problem. If I can have a lecture tomorrow. But the idea is that I want to just cover all the content as soon as possible, so that we have more time for the project in terms of revision, and also for for revision, and also for assistance with the project if things may be. After this, we're going to do like the contact ratio interference stuff, and then into gear forces immediately. That's the next part now. But I really want you guys to is go over your gear trains. That is on you. Go to the textbook, do any problems similar to this, do at least 2 of them. That should put you in a good space. Then at least you have some ideas of certain terminologies. But what is important, let me just go to the textbook before I close the lecture, is the following. Where is it? Yeah. So the main stuff you must go over, right? This is all the preamble before design gears, but what I really want to emphasize for this chapter is you need to know is from 11.7 to 11.11 is a key part of the chapter. This here is the key part of this whole thing. So these are the main parts. This must be mastered, and all these examples here is legit the important parts of this chapter. So I recommend you if you want to work ahead, focus on that, because if you know this part, it's kind of repeating in all the other chapters. It's the theories is roughly the same, just with new formulations and stuff. So that's that. And then also for the midterm, right? Just as a quick hint, nudge, is for shafts. The only thing which I think is important is just have a good understanding of your endurance limits and understanding this part over here. Just know these formulas. Make sure you know this part over here, your max, your min, and your alternating moment. This is going to help you in the test. I know I've mentioned that you can approximate it to these, obviously. So if you can know this as a start and this, that will assist you. So just treat that as the one. The other thing which I want to bring up here, which we didn't really touch on, but it's yeah. Make sure you just aware of your heat dissipation. Everything else, like I've mentioned before, if you've done it, all these things are all relevant using your charts. But your heat dissipated is another importance. And with this one, I mean, it's probably like a 2 or 3 mark question. But just know that the surface area of the housing, right? And it's estimated to be 12.5 times the actual area. So this is also important for the up and coming midterm. That being said, thank you guys. And let me know about tomorrow so we can move. And then, yeah, otherwise, I'll see you next week. And all information will be shared regarding midterm. I'm not sure what's going on myself, but let's take this opportunity to just cover everything so that things are sorted. All right, guys. Thank you.
I think I
Is
might
there any
have,
questions? Is there any questions before I close the meeting?
yes, I think I have 4 questions, but they are short. 4 questions.
Sorry?
Yeah. I think I have 4 questions, but they are short. They are
Okay,
not
CJ,
long.
what you can do, just email me the questions and I'll respond to each one. No?
Yeah, all
That's
right.
fine? Yeah.
Right.
Okay, guys. If it's a lot of questions like that. Okay, guys, thank you very much. And just keep practicing. And yeah, I'll see you when I see you. Cheers, guys.